So I just want to walk through the process of a hypothesis test again. Just because we're covering a lot of stuff, we won't have as much time for the kind of the on your own. So normally I do a few examples and let you guys try to solve it on your own. I think maybe for today I'll just walk through some examples again and just make sure that the process makes sense, okay? All right, so here's an example, okay? So let's say it is known, it is quote unquote known something is funny here. Okay. That 47% of voters actually voted in the, we'll say, latest election. Okay. This is just, we're just making stuff up here, okay? But so we're going to say it's known that 47% of voters actually voted in the latest election, okay? And a researcher is curious if the percentage of people who voted is different for people studying political science. Okay, so is it different for those studying political science? Okay, so notice that it says different. It's not, we're asking, is it greater than 40% or is it less than 40%? We're just asking, is it different, okay? And the data that that the researcher collected is that she surveyed, we will say, 54 randomly selected people, or randomly selected political science majors. Okay, and 40 of them voted. Okay, and so our question is, does our data provide evidence that the proportion of voters is different than 47% for political science majors? Okay, so this is the setup here. Okay, and so we're going to turn our question, our research question, into a pair of hypotheses that we can test. Okay, and so the null hypothesis is P is equal to something, and then the alternative is going to be P either not equal, greater than, or different from that. Okay, so we're going to, for the null hypothesis, what are we going to use as the value in our null hypothesis? Is P the proportion of voters equal to 47%, okay? And in this case, what is P? P is the proportion of what? Okay, but not just voters, but what political science majors who voted, right? Yes, that is correct. Okay, so P is the proportion of poli-sci majors who voted. Okay, and we want to know, is that the same as the general population? We know that the general population, only 47% voted. Okay, so in the general population, we know it's 47%. We want to know, is that proportion the same for poli-sci majors? Okay, and so in one hypothesis, we're saying, yes, it's the same. It's 47%. And in the other hypothesis, we're saying what?
It's not the same?
It's not the same. We're saying it's different from 47%. Okay, and that's because the question just says, is it different? It doesn't say, if the question said, does it provide evidence that the proportion of voters is greater than 47%, then we would put a greater than sign. If it says, is it evidence that the proportion is less than 47%, then we would use less than. Okay, but because the problem says different, this means we use a not equal sign. Is that okay with everybody? Okay. So because the question asks if the proportion is different. I don't need to put it in quotes. Okay, and so now we look at our data and we're going to calculate our p-value. Okay, so let's find the p-value. And so finding the p-value involves the standard error, which is p0 times 1 minus p0 over the standard, over n. And then getting our z-score, which is p hat minus p0 divided by the standard error. And then getting our p-value, which comes from the table. Okay, so let's do some work over here. What is p hat? P hat is the proportion that we observed in our sample. So we look at our data and we say she surveyed 54 political science majors, and how many of them voted? 40. So our p hat is going to be 40 divided by 54. So let's figure out what that is. We get 0.7407407407. Okay, so I'm just going to write 0.7407. Sure. Okay, so my standard error I'm going to use what? P0 is so I got to just fill in these numbers, right? Yeah, P0 is the number in our null hypothesis, 0.47 times 1 minus 0.47 divided by n. What is n? 54. It's the size of our sample. So I'm going to do this, 0.47 times 1 minus 0.47 divided by 54. And I take the square root of that. And I get 0.0679187. Okay, so I'm going to just write, this is 0.0679. That's my standard error. Okay, and so my z-score is p hat. What's p hat? 0.7407 minus p0, 0.47 divided by 0.0679. Okay, now depending on your rounding, I'm going to leave this in here, but I'm going to put in 0.7407 minus 0.47, and because I already have 0.0679 whatever in here, I'm just going to divide by the answer. Okay, so I get 3.9856. Okay, so I'm just going to round off to 3.99. This is my z-score. Okay. So notice what's happening, right? When we surveyed the political science majors, we found that 74% of them actually voted. Okay? Now, if the null hypothesis were true, if political science majors in general voted only 47% of the time, or only 47% of political science majors voted, it's technically possible that a random sample of 54 people gave me 40 voters, but that seems to be rather unlikely. Are you having a problem there, Sergio?
Oh, I think my calculator may be off, and I'm not sure why.
Okay, if you're just off by a decimal or two, it's not a big deal. If you're getting like 3.98 or 4.0 something, no big deal. Okay, so we're going to look this up here. Okay, 3.99, we're going to go to our table, okay? And if you check your notes, when you have a not equal sign in the alternative hypothesis, what you do is 2 times the tail area, or 2 times the area away from 0. Okay, so we're gonna look at this. We're at 0. We're gonna go to 3.99, and we're gonna take this area and we're gonna multiply it by 2. Okay, so let's go to our table and let's look up 3.99, and what do we see? It's not there, right? The biggest number we can look up is 3.49. Okay, 3.49 shows up as 0.9998. Okay, so 3.99 is, as we say, is off the charts. Okay, 3.99 is off the charts, but we have something very close. We have a 4.0. Okay, so I would say 3.99, that's pretty close to 4.0. And so what do we see here? We get 0.9999683. Okay, that would be the area over on this side. This side is around 0.9999683. Okay, so how much is going to be in this little piece over here? 1 minus that, right? 0.9999683. So I get 0.0000317, right? Just this ridiculously tiny number. And then according to my rules, I multiply this by 2, but as if that's going to make a difference. Okay, so I'm going to take this and I multiply it by 2. Is that okay? Then I'm taking the thing. So my p-value, so I'm taking the area in this tail, which is 1 minus 0.9999683, and I'm multiplying it by 2, because that's the rule. When you have a not equal sign, you take the area in this little piece over here and you multiply it by 2. Okay, so my p-value is this times 2, and I get 0.0000634. Is that okay? So my p-value is 0.0000634. Okay, so again, I'm gonna save this. I'll let you guys catch up in writing your notes, and we'll ask what all of this means. Monica, are you okay?
Sorry, where did you get the 0.9999683 again?
Yeah, so I'm trying to look up 3.99 in the table. I can't find it. The biggest number I can find is 3.49. Okay, so I said 3.99 is off the charts. But I have something close. I have 4.0. Right? In this little corner here, they just kind of give you some really extreme values. And so at 4.0, you get 0.9999683. That's what I'm doing. Okay? I said 3.99, somewhere around there, right? Okay. And that's how I get my p-value. We good now? Okay. So I'm going to go to the next slide. And I write my p-value is equal to 0.0000634. Okay, so what this says is that if the null hypothesis were true, that means that political science majors vote at the same rate as the general public. Which is 47%. Okay? So if poli-sci majors vote at a rate of 47%, you know, is it possible for a random sample to have a voting rate of 74%, okay, which is 40 over 54. Okay, so could a random sample produce a voting rate of 74%? Technically, yes, right? A random sample could technically produce anything because it's random, completely unpredictable. But the probability that a random sample will produce 74% if the reality is actually 47%, the probability of that happening is only 0.0000634, okay? Technically, yes, a random sample could produce a voting rate of 74%, but the probability of that happening is only 0.0000634, okay, which is pretty rare. Pretty rare. Could happen, but pretty unlikely. So rather than continue to assume that the proportion is 47%, we would say this gives us pretty good reason to doubt that poli-sci majors vote at a rate of 47%, but rather something else, probably something higher.
So it doesn't actually tell us the rate that they do vote.
It doesn't tell us the rate that they do vote, but it does tell us that I don't think this number 47% is correct. Okay? Does that line of reasoning make sense? Okay, because this is how all of hypothesis testing is done. We say, well, let's assume this statement is true. If this were true, could my data look like this? And if the answer is technically yes, but really unlikely, we're going to say, then this assumption is probably wrong. Okay? On the other hand, if it turns out to be quite likely, then we say, well, I have no reason to doubt this original assumption. Okay? Probability is only 0.000634. Okay? So my p-value is small. So I reject the null hypothesis. Okay, my data gives me reason, or as we might say, provides evidence to conclude that the proportion of poli-sci majors who vote is not 47%. Okay. So, this week, study this example. Make sure you understand it. Okay. And you'll have examples on the practice quiz to also practice. So I have another topic to cover. Okay, and this is doing the same thing, hypothesis testing, dealing with two samples. But before I go on, I just want to ask if there's any questions about, if you have any questions about this topic that I've covered so far. Yes.
The 0.999683.
Yes.
Do you subtract from 1?
Yeah, in the case, because my alternative hypothesis had a not equal sign, I looked up the number in the z table and I subtracted it from 1 to get the area away from 0, and then I doubled that.
And then you multiply by 2.
Yes, because my alternative hypothesis had a not equal sign. Okay, so earlier in the notes I said if you have a greater than sign, you take the area to the right. If you have a less than sign, you take the area to the left. And if a not equal sign, you do that thing and you multiply by 2. Okay, so you're going to have to get that in because it's going to apply to this thing and then this thing that we're going to do next. Okay, all right, so we're going to continue, and this is hypothesis testing. Okay, again, this is now, it's still 4 proportions. Okay, but now we have with 2 samples. Okay, so it's hypothesis testing, 4 proportions with 2 samples. And our research question is now asking, does this group have the same proportion as this other group? Okay, we have 2 groups and we're asking, does this group have the same proportion as the other group? And so we have 2 samples, we're going to have 2 proportions. So I will just tell you that your null hypothesis, when you're dealing with 2 samples, okay? So, well, let me just say, in the problem, you must be able to identify 2 samples. Two samples, meaning 2 sample sizes, okay? To use this method, okay? So read your problem. If you identify 2 samples, then you're going to use this method. If you can only identify 1 sample, use the other method, okay? All right, and your null hypothesis, it's always about the 2 proportions in the population. Your null hypothesis is always going to be P1 is equal to P2, okay? This can also be written okay, just doing a little bit of algebraic manipulation, subtracting P2 from both sides. So these 2 things are exactly the same thing. They might be written one way or the other. Okay, so don't, if you see it written this way, don't freak out, or if you see it written this way, don't freak out. These are saying the exact same thing. Okay, just be prepared to see it either way. And then the alternative hypothesis will be P1 doesn't equal P2, again, or greater than or less than. Okay, so any of these, okay, can also be written as P1 minus P2 doesn't equal 0 or greater than 0 or less than 0, right? Okay, so these are all, everything's equivalent. So in this sense, this method is a little bit easier just because the null hypothesis is going to be the same. Always will always be this. Once you identify two samples, your null hypothesis is always this, and your alternative hypothesis will always be one of these three. Okay, not equal, greater than, or less than. So in this sense, this step is easier. Okay, because the other one you had to figure out what your P0 was. In this case, you don't have to worry about that. Okay. The process is still the same. Once you got your hypotheses, you're going to find the p-value, and then you make the conclusion. The only thing that's different now is the formulas for finding the p-value just are ugly. Okay. So it's the only difference. Okay. The process is the same. The formulas for finding the p-value are now ugly. Okay. But other than that, it's the same process, same line of reasoning, same everything else. Okay, just the process for finding the p-value, the formulas have now gotten ugly. Okay, so step 1, get the hypotheses. Step 2, find the p-value. Okay, so we have to identify. We're gonna have to. Let me just clear out a few things, right? So our data now has two samples. Okay, so we have group 1. We'll have N1 and X1. So this is, and P hat 1 will be X1 over N1. So this is sample size, and this is the quote yeses or successes, and this is the sample proportion, right? Okay, so just finding the line of thinking is all the same. It's just the formulas have gotten a little uglier. You've got, for group 2, you have N2, X2, and P hat 2. Okay, is this okay? All right, and then we have something, so this I think is straightforward, and then we have overall P hat, and so notice that this one has neither a 1 nor a 2, and this is X1 plus X2 divided by N1 plus N2. Okay.
Call that overall P hat.
Yeah, this is our overall P hat. Or we can also call it total success over total sample size, or total observed. This is all just part of finding the p-value, okay, with the ugly formulas, which will appear on our next slide. I don't know why I'm laughing. Okay, I don't get joy out of the fact that it's ugly. It's just comical that they look the way they do. Okay, so is this okay? All right. Oh, okay. We go back. Don't worry. Ah, shoot. Crap. August. Today is August 11th. Slide 10. This is the one. Okay. So I'll let you copy that down. it's my birthday next week. Not the 18th, but the 19th. But not that you guys care. Okay.
Birthday next week.
Yeah. You can tell me next week. It'll be next Wednesday. Yeah. Yeah.
What are you gonna do for your birthday?
Probably. Well, I don't know. It's Wednesday. It's like a school night, right? So. But we're going to Vegas the weekend after. It's my wife and I are like 3 days apart for our birthdays, so we're gonna go to Vegas. Okay, anyway, well, you guys don't need to know this. All right. All right, so let's, okay, so we're gonna find the standard error and then the test statistic, and we get the area. Okay, so the standard error is p hat times 1 minus p hat times the quantity 1 over n1 plus 1 over n2. Okay? Okay, and remember, this should already be in your notes, so you might not have to rewrite it. Is that p hat is x1 plus x2 over n1 plus n2. Okay, your test statistic, the z-score is p hat 1 minus p hat 2 divided by the standard error. Okay, and then again, to get your p-value, you look up z in the z table. All right, and these rules are already in your notes, but I will write them again. If HA has greater than, take area to the right of z. Okay, if HA has less than, take area to the left of z. And if HA has not equal, take area away from 0 and multiply by 2. Same rules, okay? So this gives you your p-value. And then make your conclusion. So if p-value greater than alpha, do not reject the null hypothesis. If the p-value is less than alpha, reject the null hypothesis. Okay, so go ahead and write all of that down. Okay, next slide. Ready for an example? No, okay. Yes?
And we still assume that if the alpha...
Yeah, I'm sorry, yeah. If alpha is not specified, assume it is 0.05. Okay, and remember, alpha is also known as significance level. Okay, so let's try this out. Let's try something out here. Next slide, is that okay? All right. All right, so let's do an example. Is the proportion of men who exercise at least 3 times per week different from the proportion of women who exercise at least 3 times per week? Okay, so this is the research question that we have. Okay, is the proportion of men who exercise at least 3 times per week different from the proportion of women who exercise at least 3 times per week? Okay, so I have no idea. All right, so let's say we go out and collect data. We collect data. We survey. We will survey, let's say, 60 men and 50 women. Okay? And of the men surveyed, and again, sorry, randomly selected. Okay, so of the men surveyed, I have no idea. How many exercise 3 times per week? 20 said they exercise at least 3 times a week. I have no idea. It's different as you go from state to state. So, and of the women surveyed, I'll say 14 said they exercise at least 3 times per week. Okay, does our data provide evidence that the proportions of men and women in the population who exercise. I hate that I have to keep the writing at least 3 times per week, but you have to be specific, right? At least 3 times a week. So does our data provide evidence that the proportions of men and women in the population who exercise at least 3 times a week are different? Okay. I should have just said exercise regularly means at least 3 times per week, and I could have just said exercise regularly, and that might have been easier, but lesson learned. Okay. All right. Do you guys have all this written down? Does our question make sense? Okay, we surveyed some men, we surveyed some women. We asked, do you exercise at least 3 times a week? They say yes or they say no. All right. We're assuming everybody's telling the truth. Maybe they're not, but we're going to assume they're all telling the truth. We're assuming this is a random sample and all of that good stuff. Okay, so we're going to set up our hypotheses. Our null hypothesis is always what? When we're dealing with 2 samples, P1 equal to P2. All right. Our alternative is what? Is different. It's P1 not equal to P2. Okay? All right. So what does our null hypothesis state in words? The proportions of men and women who exercise regularly is the same. Okay, that's what the null hypothesis states. And then the alternative is the same thing, but they are different. Oh, I should say are the same. Okay. The proportions are the same versus the proportions are different. That's what they are in words. Okay, let's look at our data. Okay, so sample 1, we will arbitrarily choose to call, we will arbitrarily label sample men as sample 1, and sample 2 will be our women. Okay, what is N1? How many men did we survey? 60. How many said, yes, I exercise at least 3 times a week? 20. P hat is thus, P hat 1 is 0.333. Is that okay? All right, N2. How many women did I survey? 50. How many exercise regularly? 14. P2 hat is 14 divided by 50. What is that? 0.28. Sorry, I should have written over here, this is 20 over 60, 0.33333. Okay. So far, so good? Okay. And what is my overall p hat again? Overall p hat is equal to 20 plus 14 divided by 60 plus 50. So I get 34 divided by 110, 0.30909. I'll just call it 3091. Is this okay? Everybody happy? That's what I like to see. Okay. All right. So let's keep going here. All right. Standard error. Oh gosh, that's an ugly. Standard error is p hat overall p hat times 1 minus overall p hat times 1 over n1 plus 1 over n2. So I have 0.3091 times 1 minus 0.3091 times 1 over 60 plus 1 over 50. Okay. So let me just point out that if you take the step of kind of listing out your data and saying n1 is this, x1 is this, n2 is this, x2 is this, p hat 1 is this, p hat 2 is this, and p hat overall is this. If you take that step as you're reading the problem or after you read the problem, if you label all of these numbers, everything else will be easy, okay? If you just try to keep everything in your head, it's gonna be hard, okay? So do this step of, labeling. This is sample 1, this is sample 2, this is n1, x1, and p1 hat. This is x2, n2, x2, and p hat 2, etc., etc., etc. You do that, the rest is going to be easy. Okay, so my test statistic z is p hat 1 minus p hat 2 over the standard error. So p hat 1 was what? 0.3333 minus p hat 2, 0.28, divided by, oh, I actually hadn't figured out the standard error here, so let's do that. 0.3091 times 1 minus 0.3091 times 1 over 60 plus 1 over 50, and I take the square root of that, and I get 0.088. I'll round it to 5. Okay, and then so now I'm going to calculate this, and I do 0.3333 minus 0.28 divided by, I'm going to look up the answer key, and I get 0.60, rounded off to 2 decimal places. I get 0.60. This is my z-score. Okay, so my z-score is 0.60. Okay, so now we look up z in the table. Okay, and what do I have in my alternative hypothesis? My HA has what symbol in it? A not equal sign, right? So I take the area away from 0, and multiply it by 2. So in our case, I have positive 0.60, so I'm going to take the area away from 0. Okay, now I haven't done an example, but if I had negative 0.60, then the area away from 0 is this side, okay? So but I'm going to take this area and I'm going to multiply it by 2 to get my p-value. So my p-value will be equal to 2 times something, okay? So I will go to the table and I will look up 0.60. What is the area I find there? 0.7257, but that's the area to the left, right? So I'm going to multiply times 1 minus 0.7257. Okay, so here's a good thing. Your p-value is an area and it's a probability. So your answer can never be bigger than 1. If you forget to do 1 minus 0.7257 and you just do 2 times 0.7257 or something like that, your number will be bigger than 1, okay? And that means you did something wrong, okay? So your p-value will always be less than 1. So just a common sense check. The p-value will always be less than 1. Okay, so let's do this. We do 2 times 1 minus 0.7257, and I get 0.5486. This is my p-value. So my p-value is 0.5486. What does that mean? Okay. Oh, I forgot to say anything, but let's okay. Yeah, we'll continue to use. We will use alpha equal to 0.05. Significance level is 5%. Our p-value is 0.5486. Can I go to the next slide? Okay, so again, p-value is equal to 0.5486. Our alpha is 0.05. Okay, so this is our interpretation of the p-value, okay? So remember, the p-value, this is just the definition, the p-value is the probability of observing our data, and I have to throw in this phrase here, or something more extreme, if the null hypothesis were true. Okay, so what this means is that if the null hypothesis were true, what was the null hypothesis in our problem again? It was P1 equal to P2. And what were P1 and P2 representative of? Yeah, the proportion of men and women who exercise regularly. Okay, so if the null hypothesis were true, the same proportion of men and women exercise regularly. Okay. So if the null hypothesis were true, what is the probability that two random samples produce, you know, a proportion of 0.333 and 0.28 just by random chance? Okay, because if the null hypothesis were true, meaning the proportions are exactly the same, proportion of men who exercise regularly and the proportion of women who exercise regularly, if it's the same, anytime you take two random samples, we would expect almost the same number in our samples, right? And we're getting 33% and 28%. Okay, so we ask, what's the probability of something like this happening? And it turns out that probability is, what is it? It's our p-value. It happens 55% of the time. So observing a difference of a 5 percentage point difference is not that weird, okay? Something like that happens 55% of the time, 0.5486, just from random chance alone, okay? Well, something like this happens just by random chance, 54.86%. I should say of the time. Okay, So it's not that weird, right? That's what this is saying. It would be as if someone says, I can predict the future. Watch. I'm going to flip this coin, and it's going to land heads. And he flips the coin, and it lands heads. Are you going to go, oh my gosh, this guy can predict the future? No, you're just going to say, you just got lucky, right? The next thing you're going to do is say, well, do it again, right? Until he does it enough where you're like, oh, maybe you actually can. But if he just does it once, and he says, see, that proves it, you're not going to be convinced. You're just going to say, no, you just got lucky, okay? And that's exactly what happened here, okay? Does this mean that, when we surveyed the men and surveyed the women, one sample group said only 28% exercise and the other group said 33% exercise. Does this mean that they're different? No, it doesn't mean that they're different. On the other hand, does it mean that they're the same?
Not necessarily.
Not necessarily, exactly, okay? So we have to be very careful. We can say we do not have evidence that it's different, okay? We do not have evidence that they're different, but you cannot say this means it's the same, okay? And so, we end up in this double negative land, but we have to state it that way, okay? Because lack of evidence of something does not mean it's then the other thing. Okay. So something like this happens just by random chance 54% of the time. Okay. So our results could very well have been a result of random chance. That's what we have to write. Okay. So in short, we say our p-value is equal to 0.5486. Our p-value is greater than alpha. So we do not reject the null hypothesis, and we say we do not have evidence that the proportions of men and women who exercise regularly are different. Okay, but please note this does not mean that the proportions are the same. So we can say, or we should say, we don't have evidence that they're different. Do not say we have evidence that the proportions are the same. Okay. So we never say we accept the null. We either reject the null or we do not reject it. How are we feeling? All right, I got a thumbs up, and I have a few smiles. I don't know if these are genuine smiles of of joy or just the smile of accepting that this is the rest of your life here. Okay, at least for our class. So, okay. Anyway, do your homework. read the book, work on your practice quizzes, and we'll see you next week. And